Imagine facing a skyblack with hundreds of suicide drones. Can any weapon stop them without going bankrupt? Japan just unleashed the answer aboard the experimental warship JS Asuka. A laser that strikes at light speed, costs mere pennies per blast, and never reloads. While China's military planners have spent years perfecting drone swarm tactics, unleashing hundreds of coordinated unmanned killers to bury traditional defenses, this 100-kilowatt laser system obliterates their strategy entirely. Here is how Japan's game-changing innovation is torching the rules of naval warfare in the Indo-Pacific. For the past 3 years, naval strategists across the Indo-Pacific have confronted an escalating nightmare of drone swarms. China's People's Liberation Army has tested mothership drones capable of releasing between 100 and 150 smaller loitering munitions from internal bays. In simulated exercises conducted in early 2026, PLA naval units faced waves of low-flying suicide drones attacking maritime targets in coordinated strikes. These aren't isolated experiments. They represent a fundamental shift in how future naval battles will be fought. Traditional defenses struggle against this threat. Interceptor missiles cost anywhere from $50,000 to $150,000 per shot. When you're facing 100 incoming drones, the math becomes impossible. Shoot down 50 drones, and you've just spent $7.5 million more than the cost of the entire swarm you're defending against. Meanwhile, China continues building drone capabilities designed specifically to exploit this economic vulnerability. Taiwan has ramped up its own drone programs, recognizing these systems as critical to asymmetric defense strategies. The question became urgent. How do you stop hundreds of cheap drones without bankrupting your defense budget? But here's where it gets interesting. Japan wasn't trying to build a better missile. They were building something that makes missiles obsolete for this threat. In February 2023, Kawasaki Heavy Industries delivered a prototype to Japan's Acquisition, Technology, and Logistics Agency that would fundamentally alter naval defense calculations. The 100-kilowatt laser system combines 10 individual fiber lasers, each generating 10 kilowatts of power into a single, concentrated beam. That focused energy can burn through metal surfaces. Ground-based tests earlier in 2025 successfully engaged mortar rounds and unmanned aerial vehicles. Now, as of December 2025, that system sits aboard the 6,200-ton JS Asuka at Japan Marine United's Isago shipyard, with full-scale sea trials planned to begin after February 27, 2026. Here's what makes this weapon revolutionary. Cost per shot is roughly $1 to $10 in electricity. An interceptor missile for the same target costs $50,000 minimum. That's not a 10% improvement. It's a 5,000 to 1 cost advantage. But the economics only tell part of the story. The system operates at the speed of light, literally. There's no flight time, no interception calculation, no lead time required. Target acquisition to impact happens in milliseconds. And, unlike conventional air defense systems that carry limited magazines, 12 missiles, 24 missiles, maybe 48 if you've got a large vertical launch system, this laser weapon has what officials described as unlimited magazine depth. The only constraint is electrical power. As long as the ship's generators are running, the weapon keeps firing. That's the definition of a game changer when you're facing swarm tactics designed to deplete finite ammunition stocks. The technology behind it amplifies light through solid-state optical fibers doped with rare earth elements. It's a fiber laser system, which means higher efficiency and better thermal management than older chemical or gas-based laser designs. Japan's engineers designed modular electrical power systems, advanced beam control, and integrated cooling units specifically for maritime conditions. This isn't a science experiment anymore. It's a deployable weapons system. Ground-based trials in 2025 validated the concept against real-world threats. The prototype successfully intercepted mortar rounds, traveling at speeds exceeding 700 feet per second. It engaged and destroyed unmanned aerial vehicles during multiple test scenarios. Those aren't soft targets. Mortars are small, fast, and follow ballistic trajectories that give defenders minimal reaction time. Drones can maneuver unpredictably. The laser handled both. What happened during those tests revealed something crucial. The system's tracking and targeting algorithms could maintain a lock on fast-moving objects long enough to deliver destructive energy. A fiber laser doesn't vaporize a target instantly, like in science fiction. It concentrates thermal energy on a specific point, typically a critical component like a propulsion system, fuel tank, or control surface, until structural failure occurs. That usually takes between 2 and 5 seconds of continuous beam contact, depending on target hardness and range. But here's the kicker. 2 seconds is an eternity compared to a missile's flight time, but it's lightning fast compared to reloading and retargeting a conventional weapon. In a swarm scenario, that dwell time becomes the critical variable. Can you burn through one drone, acquire the next target, and fire again before the swarm closes the distance? Ground tests suggested yes. Sea trials will prove whether that holds true with a moving ship, ocean spray, and atmospheric turbulence degrading beam quality. The decision to move testing to the JS Osaka, a dedicated experimental platform that previously hosted railgun trials, signals confidence. Ships don't get experimental weapons installed unless preliminary results justify the investment. The system currently sits inside 2 domed modules, each measuring roughly 40 feet across. That's substantial real estate on a naval vessel, but it's scalable. Future iterations could shrink as technology matures. This is where everything changed for Beijing's naval planners. China's drone swarm strategy relied on a simple premise: overwhelm expensive defenses with cheap attackers, force enemy ships to exhaust their missile inventories, then close in with follow-on strikes. It's the same logic that made kamikaze attacks devastatingly effective in World War II. You can't shoot down everything when ammunition is finite. Japan's laser system breaks that logic. Facing 200 drones, the laser can theoretically engage all 200, as long as it has targeting data and power generation holds. The PLA's advantage in numerical superiority through mass production of low-cost drones suddenly becomes irrelevant. Each drone costs China money and manufacturing capacity. Each laser shot costs Japan pennies. The economic warfare equation just inverted. Consider the operational implications around the Senkaku Islands, where tensions between Japan and China have simmered for years. Chinese strategists have openly discussed using drone swarms to saturate defenses around these disputed territories. A single Japanese destroyer, equipped with this laser system, could establish a virtually impenetrable defensive bubble against small, unmanned threats. That doesn't stop hypersonic missiles or manned aircraft, but it neutralizes the asymmetric advantage China was counting on. There's also the matter of scalability. Japan's Ministry of Defense has indicated this technology could eventually equip the Mogami-class multi-mission frigates and Aegis-equipped destroyers. The Mogami-class frigates, already advanced platforms with Type 17 anti-ship missiles, CRAM close and defense systems, and sophisticated electronic warfare suites, would gain another layer of defensive capability. Stack that with their existing counter-drone systems, and you've got a layered defense that addresses threats from sea-skimming missiles down to small quadcopters. What keeps Chinese planners up at night isn't just one laser on one ship. It's the prospect of Japan mass-producing this technology and deploying it across the maritime self-defense force fleet over the next decade. That would fundamentally alter the balance of power in the East China Sea. Japan isn't operating in isolation. Directed energy weapons are rapidly maturing across major powers, signaling a global shift from experimental prototypes to deployable systems. The United States leads with its high-energy laser, with integrated optical dazzler and surveillance system, tested on the USS Preble destroyer, delivering up to 60 kilowatts to neutralize drones and small boats. The United Kingdom's Dragonfire laser, developed by a consortium including Raytheon and MBDA, has demonstrated precision strikes on aerial targets during live trials. Its operational cost drops to mere pence per shot, around 13 cents after a £100 million investment, making it economically viable for sustained engagement. Israel has already fielded the Iron Beam system operationally, intercepting Hamas rockets and mortars in Gaza with high success rates at a fraction of Iron Dome's interceptor costs, around $2 per shot versus $50,000. Other nations like France, with its Helma P program, and India, testing 10-kilowatt lasers on naval platforms, are accelerating development. Japan's milestone, conducting sea-based trials of its 100-kilowatt Type 42 laser on a JMSDF destroyer, stands out by bridging the gap from land prototypes to blue water naval integration, where motion, salt corrosion, and wave interference pose unique challenges. China's response underscores the escalating tensions, with the People's Liberation Army Navy conducting large-scale exercises in the South China Sea that explicitly simulate defenses against drone swarms, mirroring tactics seen in Ukraine and adopted by U.S. forces. These drills, observed via satellite imagery and PLA announcements, integrated ship-launched HQ-9B missiles, close-in weapon systems like the Type 730 CIWS, and experimental high-power microwaves to disrupt swarms at range. Electronic warfare components jammed drone command links, while DEW countermeasures, such as reflective coatings and ablative armor, were tested on mock-ups. This isn't just preparation. It's a direct counter to Japan's naval laser trials and U.S. advancements, revealing China's dual-use strategy. The same swarm offensive playbook it refined for Taiwan scenarios now demands robust shipboard defenses. This dynamic heralds the dawn of a directed energy arms race, compressing decades of technological evolution into years. Current systems like Japan's 100 kW laser prove feasibility against soft targets, drones, UAVs, and small boats. U.S. Navy's LAWS 30 kW downed speedboats in 2014 trials, while Israel's Light Sail 50 kW routinely counters artillery rockets. Power levels suffice for dwell times of seconds to minutes, but limitations include beam divergence over distance and vulnerability to weather. Expect rapid jumps to 150 to 300 kW by 2030, targeting hypersonic missiles and fighter jets. Raytheon's 300 kW class lasers, slated for U.S. destroyers, could vaporize anti-ship missiles like China's YJ-12 at 10+ km. Megawatt-class weapons, 1 MW+, by 2035, will engage hardened targets, ballistic missile re-entry vehicles, or armored cruise missiles, via sustained ablation, melting warheads mid-flight. Atmospheric challenges demand adaptive optics, already advancing via AI-driven beam focusing. By 2040, solid-state lasers will shrink to containerized units, drawing power from ship reactors. For example, Japan's AUKUS-inspired nuclear auxiliaries, reduced cooling needs via fiber lasers, and AI for atmospheric compensation will enable all-weather operation in fog, rain, or smoke. Integration with radars for 360-degree tracking creates impenetrable shields, slashing ammo costs from millions per missile to pennies per kill. The stakes are immense. The first nation to field mature naval DEWs secures a decade-long edge in carrier strike group protection and anti-access area denial dominance. Japan currently leads in maritime deployment speed, leveraging its Aegis Ashore Tech and U.S. partnerships. But China's state-driven R&D, for example, 500 kW ground tests reported in 2025, and massive shipbuilding capacity threaten to close the gap within 3 to 5 years. This race will redefine naval warfare, favoring precision energy over kinetic projectiles. The JS Asuka will begin full sea trials after February 2026. Those tests will determine whether the system maintains performance in real maritime conditions, such as salt spray, ship movement, humidity, and electromagnetic interference from onboard systems. Success means integration into active duty vessels begins within 3 to 5 years. But here's what you need to remember: this technology already works on land. The question isn't whether laser weapons can shoot down drones. It's whether they can do it reliably from a rolling ship deck in a contested battle space. And Japan's investment of 7 years of research and development through ATLA, culminating in this sea trial, suggests they have high confidence that the answer is yes. If those trials succeed, expect 3 major developments. First, Japan will accelerate production and begin retrofitting existing vessels. Second, allied nations, particularly the United States, will fast-track integration of similar systems into their own fleets. Third, adversaries will shift tactics, investing heavily in countermeasures like ablative coatings, rapid evasive maneuvers, and saturation attacks using even larger swarm sizes. The question now isn't whether laser weapons will dominate 21st century naval warfare, but when. And what happens next in the East China Sea will determine whether Japan's decade-long technological lead translates into lasting strategic advantage, or whether China's industrial capacity allows it to close the gap before that advantage matters. The clock is running, and it's running at the speed of light. Support the channel by liking and sharing this video, and subscribe to stay informed about the next wave of technological innovation.